Welcome back, calculos. Today at the DFW Academy, we will be going over separable differential equations.
And so starting off, we're going to talk about the history of differential equations. And so they were initially invented by Newton and Leibniz. And when they first discovered them, there were three types of differential equations. And so Euler actually found a few himself when he was studying the vibration of strings. And further, when studying the motion of objects in mechanical physics, they noticed that DiffEQ's could be applied to that. And that furthered the knowledge of differential equations. And lastly, Fourier discovered, because he was a chemist, when he was studying heat exchange and rate law and enthalpy, he discovered a few more. And through these three processes, we basically today have a lot more than three differential equations.
All right, now for a quick little segue, we'll come over to the applications. The applications for DiffEQ's range from radioactive decay and nuclear physics, to Newton's laws of motion, to fluid dynamics, molecular dynamics, gravity, and also engineering.
So the first type of a problem that you'll encounter when solving DiffEQ's is something along the lines of they'll give you the equation of the first derivative dy dx, and they'll give you an initial condition. And what they'll ask for is they will want you to solve for some equation y that will meet the condition of the initial condition. And so there are going to be 5 general steps to doing this. The first thing you're going to want to do is to separate your variables. And one key thing to note about this is that addition and subtraction are not allowed when separating variables. Only multiplication and division, as we'll see in the problem, are going to be allowed to separate. The second step that we have to do is we have to integrate both sides of the equation. Then we have to add some arbitrary constant c, solve for c using the initial condition, and then ultimately solve for our y equation. And so beginning to solve this problem, the first thing we're going to do is we're going to separate the variables. And so if I multiply both sides by y, I'm going to separate y to this side. So we're going to get y dy is equal to 2x to the third. And I'm going to multiply both sides by dx to move the dx. And so what we have done is we have just separated the variables. And so we did this through the process of multiplication, which is an allowable function. And so at this point, we are now going to integrate both sides. And so if we take the integral of both sides, and we're going to take an indefinite integral, which is very key to this. There's no limits of integration. And so if we're going to integrate this by hand, to do reverse power rule, we're going to add 1 and divide by the new power. And so what we're going to get is that we're going to solve for y squared over 2 is equal to 2x to the 4th over 4 plus some arbitrary constant c. And the reason we're adding our plus c is because we had no limits of integration. And so we're going to have to solve for that. And so as of now, we are now down to the 4th step, which is to solve for the initial condition. And what we're going to do is we're actually going to plug in the x and the y values they gave us in order to solve for c. And so I'm going to move right here to solve for that. So if we plug in our y value of -2, we get the quantity -2 squared over 2 is equal to 2 times the quantity 1 to the 4th over 4 plus c. And so what we're doing at this point is that we're now going to solve for c. And so what we're seeing is that -2 squared becomes 4. 4 divided by 2 is 2. So this would reduce to 2. And this side will reduce to basically 2 over 4, or in other words, 1/2, is going plus c. And so we're going to move the fraction to the other side. And so we get 2 minus 1/2 is going to be equal to c. And so using common denominators, we're going to solve for c is equal to 3/2. And so at this point, we have just met step number 4. We have solved for the initial condition. And so I'm going to move over here for the last step. We're going to be solving for y. And so we solved earlier for this equation with some arbitrary constant c. And now we have found c. And so what we're going to be doing is we're going to go back to that equation. So y squared over 2 is equal to 2x to the 4th over 4 plus 3 over 2. And so at this point, I'm going to basically multiply both sides by 2 because we want to get y by itself. And so we have y squared is equal to 2 times the quantity 2x to the 4th over 4 plus 3 over 2. And then at that point, I'm going to take the square root of both sides. But one important thing is when we're taking the square root of the square, we get the absolute value. And so we basically have the absolute value of y is equal to the square root of 2 times the, I'm actually going to distribute this 2 because I think that's going to make more sense in the long run. So if we distribute this 2, we get 4x to the 4th over 4, which becomes x to the 4th. And we get 2 times 3 over 2, which becomes 3. And then in order to get rid of the absolute value, we take the plus or minus. And so we get y is equal to plus or minus the square root of x to the 4th plus 3. So now we have solved for y, but we have to test, is it the plus or is it the minus? And so this is where the initial condition comes in again. If we were to plug in f of 1, we get that 1 to the 4th, which is 1, 1 plus 3 is 4. And so the square root of 4 is going to be 2. So we get that y is equal to plus or minus the quantity 2. But we see in the initial condition that we want negative 2. And so therefore we're going to eliminate the positive value. And so what we have essentially proven is that y is really equal to the negative square root of x to the 4th plus 3. And so these are the 5 steps that we have done to solve this differential equation for some equation y using an initial condition. The second type of problem is going to be something called an Euler's method. And so what they're going to do is they're going to say, given some equation dy dx, again with another initial condition, use Euler's method to approximate some value with so many steps of equal length. And so in this case, we were given our dy dx equation, our initial condition of f of 1 is equal to 2, and we want to approximate f of 3 with 2 steps of equal length. And so what we're going to start with is we have to find what our steps of equal length are. And so what we notice is that I'm going to define the variables to begin with. We want 2 steps of equal length, which would imply that n, some variable, is equal to 2. And so what we want to know is we are going from f of 1 to f of 3. And so we want 3 minus 1 over 2. And basically what I'm finding is the consequential change in x given 2 equal intervals. And so 3 minus 1 is 2, 2 over 2 is 1. And so what we find here is that our delta x is equal to 1. Now, I made this nice little table that Mr. Winter will show you in class. And what this is basically the Euler's method table. We're starting with x, y, dy dx, and the change in y. And the reason that I wrote this little equation is I'm going to prove this to you. We know that dy dx is the same thing as saying the change in y over the change in x. And so if I was to solve this for the change in y, multiply the change in x over, that's where this equation is coming from. And so with that in mind, I'm going to start to fill in the table. We're starting at x equals 1, then our y value is 2. And we want 2 steps of equal length, and our change in x that we found earlier is 1. So we're going to go from 1 to 2 to 3. And so now I'm going to start to fill in the rest of the table accordingly. And so we have our equation for dy dx is equal to x plus y. So 1 plus 2 gets us 3. And then we're going to multiply this dy dx by our change in x. And so 3 times 1 gets us 1. Or sorry, 3, my bad. And so what that's saying is that we're now going to add this to our y. So our change in y becomes 3. And so 2 plus 3 gets us to 5. And we're going to repeat the process all the way down until we get to the y value that we want. And so 5 and 2 is 7. 7 times 1 gets us 7. And then 5 plus 7 gets us to 12. And so using this table, let's say 12. Using this table, we basically showed that using Euler's method, we can approximate f of 3 to about 12. So this is the second type of differential equation problem that you will have to solve, and this is again called an Euler's method. Remember, kids,
A gun can blow a vato away, but calculus can blow a mind away.
See you next time at DFW Academy. See you on the flip side, nephew.